Assalamualaikum and hi everyone, I'm Madam Shafika. So let's continue lesson 13 and we are still in chapter 8, which is physical optics. And for my part, I will continue with 8.5 under subtopic diffraction by a single slit, and then 8.6 under subtopic diffraction grating. So let's start. Okay, so we start with 8.5 first, which is diffraction by a single slit. So in this subtopic, we are going to define what is the diffraction, okay? And then we are going to do some explanation with the aid of a diagram about the diffraction of a single slit. And then I will introduce to you what is the equation that related to the calculation of the single slit diffraction. So diffraction is defined as the spreading of wave after a wave passing a narrow slit or an obstacle. It is the result of interference between sources on the same wave front. So as you can see, the animation showing you that when the wave passing a narrow slit or any obstacle, so what happened to the wave? Okay. So the wave will produce the interference between the sources on the same wave front. Alright? And diffraction also defined as the bending of a wave around the edges of an opening or other obstacle. Okay. So now look at here. Let's say we have the parallel light rays come from here. Okay. So this is the light rays. And according to the hygiene principle, each portion of the slit now acts as a source of a new light. Okay, so we have 1, 2, for example. Okay, we have many source of new light wave. Okay, for example, 1, 2, 3, 4. Okay, and we call it as the secondary wavelet, where the secondary wavelet, okay, will radiate to the screen. Alright, in this direction. Therefore, the light from one portion here, for let's say for the portion 1 and the portion 2, the light from one portion of the slit can interfere with light from another portion. Okay, for example, the light from this first portion will interfere with the light from the second portion. The diffraction pattern is actually an interference pattern. Alright, so now look at this diagram. Okay, so for a single slit, we do get an interference pattern here. It's not exactly the same pattern as double slit diffraction, but still, we get an interference pattern although we only have one source of light here. Okay, so what we can see now, at the center of the pattern, we have the bright fringe with high intensity. So this showing you that at the center of the interference, or we call it center bright fringe, okay, the intensity is the highest intensity here. Okay, so the brightness of the fringe is related to the light intensity. So when you observe on the screen, the center bright fringe is the brightest bright fringe that you can observe. Okay, and here we have a dark area and then the bright fringe. And this is repeated for the other side. We have the top side and also the bottom side. Okay, so now if you look at to this diagram, okay, so A is stand for the width of the single slit, and capital D is stand for the distance between the single slit and the screen. Okay, so all the interference pattern, okay, bright and the dark fringes can be observed on this screen. Alright, so this is the central bright fringe, and YM is the distance of the first dark fringe from the center. Okay, so we will look further about this. Okay, now look at this diagram. Let's say we have a single slit here with the width of A. Okay, so we write the width of the single slit is A. So instead of thinking about all the points of the second wavelet here, let's think about one point at the upper of the slit, for example here, and another point at the middle of the slit, which is here. Okay, So the distance of these 2 points is given by A over 2. Okay, so this is A over 2. And now, let's think about what is happening over here on the screen. Means that the light from the top edges of the slit has to travel at a certain distance to get on the screen, while the light that comes from the middle of the slit has to travel at a different distance. So, if the path difference, so you can look at here, if the path difference, okay, so let's say this is from the top of the edges and this is from the middle. Okay, so the light from the middle will travel with a different distance compared to the first one. So if the path difference is a half wavelength here, means that these two waves travel with a different distance. So they will get the cancellation, okay, on the screen, and we will get a dark spot. Conversely, when the light from the top and the bottom edge that travel with the same distance, okay, interfere, and they're gonna arrive here in phase. Okay, so here they are in phase. But for this one, they travel with a different distance. So when these two light interfere on this point, so there is a phase difference. Okay, there is a phase difference between the first ray from the top of the slit and the second ray from the middle of the slit. Okay, so what happened? Oh, sorry. Okay, so now, so you can look at here, we have a constructive interference. Let's say we have the first ray from the top of the slit and this is from the bottom of the slit. Okay, so what happened? These two rays gonna arrive on the screen in phase, and then the bright spot or the bright fringe will produce. Okay, so now let's focus about central maximum. So according to the Huygens principle, every part of the wavefront in the slit will emit wavelets. Okay, so we're assuming the screen is very far away compared with the size of the slit here. Okay, and rays heading toward a common destination are nearly parallel. Okay, so when they travel straight ahead, as in this diagram, they remain in phase and a central maximum is obtained on the screen. However, if you look at to the diagram B, C and D, so when rays travel at angle of theta relative to the original direction, so we assume the original direction is parallel to the right, so each travels at a different distance to a common location. And what happened? They can arrive in or out of phase on the screen. Okay, so if you look at to the diagram B here, so the ray from the bottom travels at a distance of one wavelength farther than the top ray. So when two rays arrive in phase, means that the bright fringe will observe on the screen. When these two rays arrive out of phase on the screen, means that the dark or the destructive interference will observe on the screen. So now look at to the figure 1 here. Okay, we notice that there are the additional bright spots on the screen, but the intensity of these bright spots is a bit less compared to the central maxima here. Okay, so figure 1 here represents the intensity of the orders as we move further from the bright central maximum. Then figure 2 here showing the real pattern of the interference on the screen, and as you can see, the intensity of the bright fringes are different compared to the central maximum here, since this bright fringe has the highest intensity compared to the other bright fringes. Okay, so now let's move to the next part, and this is about the dark fringe. Okay, we will look at how dark fringe can be produced on the screen. So here we have a diagram of a single slit, and we divide the slit into half, and this we call it as the upper zone, and this is the lower zone. Okay, so let's say this is the upper, so let's say this is the upper zone and this is the lower zone. Okay, so look at here, we have a plane of the wavefront at a slit of the width A. Okay, and let's points on the wavefront are labeled as 1, 2, 3, 4, 5. So as we know, here we have a lot of wavefront here, okay, that acts as the second wavelet. But now we just consider point 1, point 2, point 3, 4, 5. Okay, and each point here act as a source of a light wave. Okay, so these different light wave will interfere. For example, wave 1 and wave 3 will interfere and produce interference pattern on the screen. So let's find the first minima above the midpoint by pairing up rays from the top point or the upper zone. Okay, the top point of the top zone. Okay, so here is the top point of the top zone. Okay, and also the point from the top point of the bottom zone. This is the top point from the bottom zone. Means that now we are pairing up the first ray and the third ray. So you can see here, wave 3 travel farther than wave 1 by A over 2 sine theta. Okay, if we draw the line here, okay, so let's say we draw a line here. So let's say this is the 90 degree and this is the angle theta. Okay, so this is the path difference. That's mean wave 3 will travel farther than wave 1 by this amount of x. Let's say we name it as x. Okay, so when we focus on the triangle here, okay, so this we call it as the path difference. Okay, awak tengok kat bawah ni. So we call it as the path difference. So when we write sine theta, okay, is equal to, since we denote this as x, so sine theta is equal to sine theta is equal to x over A over 2. Okay, since the hypotenuse of the triangle here is A over 2. So rearrange this equation, we will get, okay, the path difference. Okay, so the path difference is equal to A over 2 sine theta. Okay, because x is the path difference, so the path difference x is equal to A over 2 sine theta. Therefore, wave 3 will travel farther than wave 1 by A over 2 sine theta. And this is the path difference. Same goes for wave 4 and 2. Okay, so if the path difference between wave 1 and wave 2, okay, is equal to lambda over 2, okay, you can see here, when the path difference of these two waves is lambda over 2, these wave pairs will cancel each other when they arrive on the screen. Let's say this is the screen. So what happened? On the screen, we will observe the dark spot or the dark fringe because the destructive interference happened on the screen. Therefore, we can write as the path difference. Okay, so the path difference is equal to A over 2 sine theta is equal to lambda over 2, where lambda over 2 is the path difference of the two waves that will cancel each other on the screen. And for the first dark, we can write A sine theta is equal to lambda. Okay, because we cancel this one. Therefore, if wave 1 and wave 3 are interfere, okay, they will produce the first dark fringe on the screen. Okay, so this is another example, okay, of the diagram. So this one is the bigger diagram. So D, the capital D, is the distance between the slit and the screen. So now at point P, you can see here, okay, this pair R1 and R2 will cancel each other at P1. So do all such pairings. Okay, so what we can observe at point P here is the dark fringe. Okay, the first dark fringe. And this is the path difference of X. Okay, yang kita dah discuss tadi. So the first minimum or the first dark is equal to A sin theta equal to lambda. Alright. So let's look at the second minimum or the second dark. So now for the second minimum, we divide the slit into 4 parts. Okay, we divide the slit into 4 parts. So we have part 1, part 2, part 3 and part 4. Okay, so where the distance from the first ray here, okay, with the distance from the second ray here, so the distance is A over 4. Okay, so when ray 1 and ray 2 arrive at point P2, you can see the path difference is lambda over 2. Since on P2, we can observe second minimum. Okay, so when we write the equation, so for the path difference between R1 and R2, so this is ray 2 and this is ray 1, and the path difference between them is right as X. Okay, means that R2 will travel farther compared to R1 by X. Okay, so when we observe second minimum on point P2, means that the path difference, okay, the path difference X is equal to, okay, so this is the angle, so sin theta is equal to, we can write as sin theta is equal to X over, sin theta is equal to X over A over 4. Therefore, X is equal to A over 4 sin theta. Okay, so this is the path difference between R1 and R2. So if on point P2 is the second minimum, that's mean the path difference between R1 and R2 is lambda over 2. And when R1 and R2 interfere on the screen, so they must be out of phase by lambda over 2 at screen. Therefore, the second minimum will be produced on P2. And we can rearrange this equation, and the equation for the second minimum can be write as A sin theta equal to 2 lambda. Okay, so this one we can cancel. Okay, and then bring 2 to the other side. So you will get A sin theta is equal to 2 lambda. Okay, so when we compare equation of the first and the second dark fringe that we have discussed just now, we can see that for the first dark fringe, where there is a path difference of A sin theta between the first ray and the second ray, okay, so the equation can be write as A sin theta is equal to lambda. So for the second dark fringe, after the derivation, we will obtain the equation of the path difference between ray 1 and ray 2 is A sin theta equal to 2 lambda. And when we try to derive the equation of the third dark fringe, we're gonna have equation of A sin theta is equal to 3 lambda. Therefore, so in general, the dark fringes are produced when all the rays interfere destructively. So the destructive interference will happen when the path difference between the rays are equal to A sine theta equal to M lambda, where M is the number of order. Okay? So this is the first dark fringe, means that the order number is M1 for the dark fringe, and second dark is M is equal to 2. So for the third dark, the equation will be A sine theta is equal to 3 lambda, where M, the number of order, is equal to 3. Okay, so this is the general equation of the destructive interference or the dark fringes equation. So now we are going to discuss the distance between dark fringe to the central bright. For example, okay, we want to calculate what is the distance. So now we are talking about this distance. We want to calculate what is the distance from the central bright here to the first minimum or the first dark spot here. Okay, and we put the symbol as YM. It stands for the distance between M dark fringe to the central bright. Okay, so since we know that in general a minimum or the dark fringe is obtained at angle of theta. Okay, and this is the equation that we have discussed just now, where M is the number of order. So positive, negative 1, positive, negative 2, positive, negative 3. Why we have positive and negative order number? Because we have two sides, which are the top side and the lower side. Okay, so this is, let's say this is the positive M. M is equal to 1, and this one is negative 1. That's why we have two signs for the order number, which are positive and negative signs. Okay, so A is the width of the single slit, where theta N is the angle for the M minimum measured from the central axis. So if we want to calculate at what angle the first dark fringe will be observed on the screen, so this is the angle that we need to calculate. Alright, and lambda is the wavelength of the monochromatic light that we use in this experiment, for example. Okay, so look at this angle. Okay, so now let's highlight the triangle. Okay, so this is the triangle that we are going to discuss. Okay, this one, the blue color. So now we are focusing on the YM. We want to calculate what is the distance between the central bright to the first dark. So it's a YM. Okay, so let's say we write as tangent theta. So we look at to this triangle. So tangent theta is equal to YM over D. So from here to here is D. So tangent theta is equal to YM over D. Alright, so since the angle theta is very, very small, thus we can write that if tangent theta is equal to YM over D, if this angle is very small, we can write that sine theta is equal to, okay, and you can see if this angle is very small, so the hypotenuse is close to the value of D. So we can also write sine theta is equal to tangent theta. Okay, therefore from this equation, okay, we have sine theta is equal to M lambda over A. Okay, so sine theta is equal to M lambda over A. Therefore, since sine theta is equal to tangent theta, so sine theta is equal to M lambda over A, while tangent theta is YM over capital D. Therefore, we can rearrange this equation. YM is equal to M lambda D over A. So in order to calculate the distance of the first dark fringe, for example, we can calculate the distance of the first dark fringe from the central bright. Y1 is equal to 1 lambda D over A. So we need to substitute the value of lambda D, and also the width of the slit. Okay, so this is the general equation of the YM for dark fringe. Alright, so okay, so now we are going to discuss the relationship between YM and D, YM and A, and YM and lambda. So let's erase this first. So if you look at this equation, we can straightly relate the relationship between YM and lambda, YM and D, YM and A. So YM and D is directly proportional. So when the distance of D is increasing, so you can see here, when D is increased, okay, YM also increase. So means that the interference pattern will become wider. Okay, kalau ini from the central bright fringe to the first minimum semakin jauh, then from the central to the second minimum also become farther away. Okay, so what happened to the interference pattern on the screen? The interference pattern become wider. Alright, so for the second relationship, YM is inversely proportional with the width of the slit. So if the width of the slit is increased, when A is increased, we will see the pattern. Okay, YM will be decreased, and then we will see the pattern of the interference become narrower, because YM, the distance between the first minimum and the second minimum also become closer to each other. The distance between the central bright and the first minimum will become closer to each other. Alright, so the third relationship is between YM and lambda, where YM is directly proportional with lambda. So when the wavelength is increased, the value of the YM also increase. Means that the distance between the central bright fringe and the first minimum will become wider. And what happened to the pattern of the interference? The pattern will become wider. Dia semakin jauh lah, the first dark and the second dark, and the third dark, and so on. Okay, now we are going to discuss about the bright fringe in the single slit experiment. Okay, so for the bright fringes, okay, bright fringes are produced when all the rays interfere constructively. So previously we have discussed about the dark fringes, where the dark fringes are produced when all the rays interfere destructively. But for the bright fringe, all rays interfere constructively. Okay, so the path difference between ray 1 and ray 2 is given by A sin theta equal to m plus half lambda. Okay, so the points of constructive interference lie approximately halfway, or we call it as midway, between the dark fringes. Means that, okay, look at here, we have this is the central bright fringe, okay, and Y1 is stand for the first dark. Okay, so sorry. Okay, so this is the first dark, and this is the second dark. So the first bright fringe can be obtained at the midpoint between the dark fringe. So we have first and the second dark fringe, where so the position of the bright fringe should be at the midway, okay, between the first dark and the second dark, which is at this position, and this is first bright. Okay, let's say we want to calculate what is the distance of the first bright from the center bright fringe here. Okay, so I write this one as Y1 bright, so that I know the blue color here is the distance from the central bright fringe to the first bright. Okay, so let's recall from the previous part, we have discussed about the distance of the dark fringe, or the minima, from the central maximum, and the equation is given by Ym. So the general equation is Ym, this one is for dark, is equal to m lambda d over A. Okay, then the distance of the first and the second maxima from the 0th order maximum. Okay, the 0th order maximum, we can call it as the central bright fringe. Okay, so this is the central bright fringe. Okay, and then the distance of the first and the second maximum from the 0th order is given by this equation. This is the distance from the center to the first bright, and this is the distance from the center to the second bright. Okay, so now if the distance from here, from 0 to y1 dark, is lambda d plus a, therefore 1y bright can write as equal to lambda d over a plus, okay, lambda d over a is the distance from here to here, and from here to here also lambda d over a. Okay, so we know that from here to here is lambda d over a. Okay, so here to here is lambda d over a, and from here to another dark fringe is lambda d over a. So that's why y2 second dark is equal to twice lambda d over a. From the center, lambda d over a plus lambda d over a. So y2 dark is equal to 2 lambda d over a. Therefore, the distance of the first bright here, okay, you can see here, this is half. Okay, this is the midpoint from y1 to y2. So means that from 0 to y1 is lambda d over a plus half lambda d over a. Okay, since the first bright is at the midpoint of y1 and y2, so we need to plus half lambda d over a. Therefore, we can write y1 dark, therefore we can write y1 bright is equal to, okay, we can factorize 1 plus half lambda d over a. Okay, and when we try to derive for the second bright, so the distance from the central maxima to the second bright, it's going to be 2 plus half lambda d over a. And in general, the distance of m order for the bright fringe to the center means that from 0 to the first bright fringe, or from 0 to the second bright fringe, or from 0 to the third bright fringe, we can calculate the distance between the central bright fringe to the m order bright fringe by using this equation, which is ym is equal to m plus half lambda d over a. Okay, so now this is the diffraction pattern. So let's try to look at this pattern in order to discuss about the width of the central bright fringe. Okay, so based on this diffraction pattern, we can see here at the middle of the interference pattern, there is a central maximum, where the central maximum is start from here to here. And this is the y1 dark. Okay, so y1 dark is measured from the center of the central maximum. Here, y1 dark. Another side is also 1y dark. So in order to calculate the width of the central bright fringe, this is the width of the central bright fringe, and we put as W. It's actually twice the y1 dark. Okay, so from center, okay, we can measure or we can calculate y1 dark by using this equation, which is m lambda d over a, where 1 is the first order times lambda d over a. Okay, and since we have two sides, the upper side and the lower side, so the width of the central bright fringe can be written as y, so W is equal to 2 times Y1 dark. Okay, so we have the first dark fringe for the upper side and the first dark fringe for the lower side. Okay, so since this is the position of the first dark, so this is Y1 dark, so this is the position of the first dark for the lower side. Okay, so we need to add up the Y1 dark upper side with the lower side. Therefore, the width is equal to 2 lambda d over A. So if you read here, we have a width of the central bright goes from the first minimum on the one side to the first minimum on the other side. So the general equation is 2 lambda d over A. And the most of the light intensity is concentrated in the broad central bright fringe. Means that the highest intensity of the bright fringe is at the central maximum. Okay, in the forward direction, since all the rays that travel in the central maximum is equal to, the angle is equal to 0 degree, means that all waves interfere constructively and giving maximum intensity at the center of the diffraction pattern. Alright? Okay, so now look at the relationship between the width of the central bright fringe W with the D. D is the distance from the screen to the single slit. Okay, so since they are directly proportional, so means that when D is larger and W will become bigger, means that more wave will be spread out. Okay, so the pattern will become wider. Okay, but the relationship between A and W is inversely proportional. When the slit, the width of the slit is become narrower, what happened to the W? W will become larger. Okay, sama lah. Then more wave will be spread out. Okay, so this is wider. The diffraction pattern will become wider. So now W is directly proportional with lambda. So when lambda is increased, so now W is also increased. So the interference pattern also become wider. Okay, alright. So this is the summary of this part, which is 8.5. So the diffraction of single slit. So we have constructive interference, and this one is the equation of the path difference, and we have Ym. This is the equation of the distance between the M order of the bright fringe to the central bright fringe, and this is the equation for the destructive. And the last one we have covered about the width of central bright fringe. Okay, so the number of order, remember for the single slit we have first dark, first bright, second dark, second bright, third dark, and then third bright. And the center bright, we call it, when M is equal to 0, we call it as the central bright fringe. Okay, so the central bright fringe at the center of the interference pattern, okay, the order is M is equal to 0, not the first order of the bright fringe. Okay, don't be confused. Okay, so A is the width of the slit, M order, lambda is the wavelength, D is the distance between slit and the screen, Ym is the distance between M bright dark fringe to the central bright, and the last one is the angle. Okay, so this is the difference between diffraction and the interference pattern. So we have the single slit diffraction pattern, okay, and then the double slit interference pattern. So here is M is equal to 0, and here we call it as the central bright fringe. Okay, so the width is non-uniform. As we can see here, the width of the central bright fringe should be bigger compared to the other width of the bright or the dark fringe. But for the double slit, we have the uniform width. Okay, and the central bright fringe is twice as wide as the other fringes. Yes, we have discussed before. and all the fringes have equal width. Okay, we don't have the central bright fringe for this one. So the intensity of the zeroth order maximum, which is the central bright fringe, should be much higher than the other maxima. Okay, so here we have m equal to 1, m is equal to 2, and we call here is m is equal to 0. Okay, where the intensity at the central bright fringe is much higher compared to the m1 here and also m2 here. Okay, and for the double slit, okay, we can see that the neighboring maxima have the same intensity. So now we have finished the first part, which is subtopic 8.5. So now let's proceed to subtopic 8.6, which is diffraction grating. Okay, so we are going to discuss about the formation of diffraction with the aid of a diagram, and then apply the equation of d sine theta equal to m lambda, okay, where d is equal to 1 over n. Okay, so if you can see here, the definition of the diffraction grating, so it's actually a device consisting of a great number of narrow, closely spaced, equidistant and parallel slits or lines. So you can see here we have a lot of lines here, and it is a parallel slits. Okay, so the equation of the grating spacing d is given by 1 over n. Okay, in order to calculate the grating spacing, okay, between the lines here, we can calculate by using equation 1 over n, where n is the number of lines per unit length. Okay, so in your experiment, you are going to use this diffraction grating, where here we have 100 lines per millimeter, and 300 lines per millimeter, and 600 lines per millimeter. So in order to calculate the grating spacing, we can use this equation where d is equal to 1 over 100 lines per millimeter. Okay, so the unit in millimeter, make sure you beware about the unit and make sure your calculation in SI unit. So this is the diagram that explains about the constructive and destructive interference in diffraction gratings. So as we know that the diffraction grating consists of a large number of equally spaced parallel slits, okay, and a typical grating contains several thousand lines per centimeter. So in your experiment, we use 100 lines per millimeter, or 300 lines per millimeter, or 600 lines per millimeter. Okay, so the intensity of the pattern on the screen here is the result of the combined effects of interference and diffraction. Okay, so you can see here, each slit produces diffraction, and the diffracted beams interfere with one another to form the final pattern on the screen. So on the screen, you can see here we have the central or zeroth order maximum. So this is the bright fringe, where the order number is m is equal to 0, and this is m is equal to 1 for the first order maximum. Okay, and for the other side also we have the first order maximum, m is equal to 1. Okay, so here is the real interference pattern of diffraction grating that you can observe on the screen. Okay, so you can see we have a different views of the diffraction pattern. Okay, so we will discuss about it later. Okay, so let's proceed. So the formation of diffraction. So now look at here. Okay, based on this diagram, you can see here we have the monochromatic light, where the monochromatic light strikes a diffraction gratings. So this is the diffraction gratings. And as we know that the diffraction grating consists of thousands of slits per centimeter. Alright, so according to the Huygens principle, each point on the wavefront striking the slit acts as a point source of a secondary wavelet. Okay, and what happened after passing through the diffraction gratings? All the wavelets, all the lights is diffracted at angle of theta. So the diffraction pattern is observed as shown in the figure. So when all the secondary wavelet is diffracted on the screen at a certain angle of theta, which are theta 1, theta 2, theta 3, then you can observe the diffraction pattern on the screen. Okay, so we have the centered bright here, and we call it as the zeros order for the bright fringe, M1, M2, and so on. Okay, so the bright fringes are observed when all the rays interfere constructively in phase. The rays interfere constructively in phase with path difference equal to m lambda. Okay, so now look at to the further explanation. So you can see here, okay, the path difference between the neighboring wavelets is equal to d sine theta. Okay, so let's say we take ray 1, okay, ray 2. Let's discuss about these two rays. Okay, you can see here the path difference, the green color here. Okay, let's say here is D. Okay, here is T. Okay, so this is the path difference X. Okay, so this is the angle of theta. So when we write the sine theta is equal to X over D. Therefore, the path difference, let's say we call it as X, is equal to D sine theta. Okay, so for the constructive interference to be happen on the screen, the path difference here is equal to m lambda, and it's equal to D sine theta. Alright, where m is the number of order, d is the grating spacing, where it's equal to 1 over n, and angle theta is the angle of the m bright fringe. For example, the position of the first bright fringe here, m equal to 1, is happen at angle of theta 1. But for the second order, for the bright fringe, it can be produced when the angle is equal to theta 2. Okay, and then we can calculate the other angle for the other order of the bright fringe. Alright, and m is the number of order, lambda is the wavelength of light. Okay, okay, so this is the another look of diffraction gratings. So as we know, for a given wavelength, a special angle will result in constructive interference. So this is the equation tadi. This angle is different for different wavelength. So you can see it also depends on the wavelength. So when we rewrite the above equation, we can write theta is equal to inverse sine m lambda over d. Let's say we want to find what is the angle of theta when, let's say, when m is equal to 3. So we can substitute in this equation where m lambda over d. Okay, so m is equal to 3. So now, based on this equation, we can calculate at what angle the third order of the bright fringe can be observed on the screen. Okay, alright. Okay, now look at this part. The highest number of order that can be observed is limited by the fact that theta cannot be more than 90 degree. So logically, if we draw the lines of rays here, okay, so let's say the rays here can produce the third order of bright fringe, the fourth order, the fifth order, and seterusnya. Okay, so the maximum angle is equal to 90 degree. So logically, theta cannot be more than 90 degree. Okay, because sin theta must be less than 1.0. So in order to calculate what is the highest order number, okay, that we can observe on the screen. For example, this is m equal to 3, m equal to 4, m equal to 5, and so on. So we want to know what is the highest order that we can observe on the screen. We can write as sine theta less than 1. Okay, means that the angle cannot exceed 90 degree. Okay, so based on the equation, sine theta is equal to m lambda over d, and rearrange the equation, we will get the new equation M, the number of order, is equal to D over lambda. So the highest number of orders possible is given by the highest integer that is less than D over lambda. Okay, so if we do our experiment, the number of order that we can observe on the screen depends on lambda and also depends on D, where D is the spacing gratings. Okay, where D is equal to 1 over N. So now, let's look at the relationship between M, D, and also M and lambda. Okay, so we can see here the number of order M that can be seen on the screen depends on, so this is very important. So you can see here where M depends on N, because D equal to 1 over N, where N is the number of lines per millimeter, okay, and D, or we call it as the grating spacing, N, okay. And you can see here, if the number of N, okay, when N is bigger, what happened to the order number that we can observe on the screen? It's become smaller, okay, because when this one is bigger, and this is become smaller. When D is become smaller, and M will become smaller. So look at here, we have figure ABC, and from here you can see we have a different pattern of the interference pattern. Okay, alright. So let's discuss about relationship between M and N first. Okay, alright. So now for the first example, okay, so when we look at to the number of lines per millimeter, when the number of lines is bigger, so the value here should be lower. The grating spacing should be lower. Okay, so when the grating spacing becomes smaller, since M is directly proportional with D, so M also become lower or smaller. Okay, so let's say here, we have at the center here, we have 0th order. M is equal to 0. So now let's compare. If we use the diffraction grating with 100 lines per millimeter, so when this one, when N is become smaller, the value of D, grating spacing, will become bigger. Okay, as M is directly proportional with D, when D is increased, the number of order also increase. So here you can see, here we have M is equal to 0, and this is M is equal to 1, M is equal to 2, 3, 4, and 5. On the screen, we can observe up to 5th order of the bright fringe. Okay, so now when we try to increase the number of lines per unit length with 300 lines per millimeter here, so what happened? Okay, so back to this relationship, when the number of lines per unit length is increasing, the order number should be reduced. So now we can only observe up to 4th order number, 1, 2, 3, and 4. Okay, and the last one, when we try to increase to the another number, which is N is equal to 600 lines per millimeter, therefore here we can observe up to 3rd order only. Okay, so this is the relationship that you must know, because this is very important. Okay, now look at this question. What is the difference between maximum number of order obtained and number of maximum that can be seen on the screen? Okay, let's write the first one. Okay, what is the difference between maximum number of order? Maximum number of order obtained on the screen. Okay, so what is your answer here? And second is the number of maximum. Okay, the number of maximum that can be seen. seen on the screen. Sorry for the bad writing. So maximum number of order obtained on the screen. Okay. So maximum number of order obtained on the screen can be calculated by this way. Okay, it's a maximum number of order. So for example, if we use n equal to 100 lines per millimeter, so the maximum number of order obtained on the screen is up to the 5th order. Okay, so the answer is equal to m equal to 5. Okay, but if the question asks you to find the number of maximum that can be seen on the screen, means that how many bright fringe or the bright spots that you can see on the screen. Okay, so here we have 1, 2, 3, 4, 5, and let's say we put a number here. 1, 2, 3, 4, 5. So this is for the one side, for the right side. And how about the left side? We also observe up to 5th order bright fringe. 1, 2, 3, 4, 5. So for example, we can observe up to 5th order. So maximum number of order obtained on the screen is 5. Means that 5 on the right side and the 5 on the left side. But remember, at the center here, we have another bright spot. Okay, so the total number of maximum that can be seen on the screen is equal to 5 plus 5 plus 1. And the answer is equal to 11. Okay, so the number of maximum that can be seen on the screen is 11 bright fringe, 11 dots. Okay, so we need to consider both sides, left and right, okay, in order to calculate what is the maximum number of the bright spots that we can see on the screen. Alright, next is the number of order. M also can depends on the wavelength. So second is the wavelength. So you can see M is inversely proportional with lambda. Okay, so let's discuss. Alright, so now you can see here when the value of lambda is increasing, since lambda is inversely proportional with M. When lambda is increased, so M will be decreased. The number of order will be reduced. For example, here we have 3 types of color with a different wavelength. So purple, green, and red. So let's say the wavelength of the red color is 670 nanometer, and green color is 532 nanometer, and purple is 400 nanometer. So on the screen, we can observe a different pattern of the interference. Okay, so when we increase the wavelength of the monochromatic light that we use, the order number that can be observed on the screen will be reduced. So this is the table of the order number for diffraction grating. Okay, so for the diffraction gratings, we have the zeroth order maximum, M equal to 0. Okay, and at angle of theta 1, we will observe the first bright fringe or first order maximum, and at angle of theta 2, we will observe M is equal to 2. Okay, so in order to calculate what is the maximum order that we can observe on the screen, for example, okay, so we need to calculate the number of order by using equation. Okay, so one of the application that we can observe in our daily life is on the compact disc, okay, where the compact disc is act as a diffraction grating. Okay, where the surface of a compact disc has a spiral groove track with adjacent groove having a separation on the order of 1 micrometer. Okay, so the surface of the compact disc acts as a diffraction grating. Okay, so when the compact disc is viewed in white light, so what happened? Okay, the light reflecting from the regions between this closely spacing groove interferes constructively in certain direction. Okay, so another explanation. Okay, let's say we have the tracks of a compact disc. Okay, as we know, the compact disc can act as a diffraction gratings, and it can produce a separation of the colors of white light. Okay, and yeah, so this is the extra information for you. So for red light of wavelength 600 nanometer, this would give a first order diffraction maximum at about 22 degree. Alright, so I think that's all from me. So thank you. So we have finished chapter 8, and we will continue with lesson 14 with chapter 9. Alright, so thank you. Assalamualaikum and selamat sejahtera.